Part 3, Hypothesis Testing. I'm Dennis Davis. In Video 1 on the sampling distribution, we considered a population and described the characteristics of a sample drawn from it. In Video 2 and 3, we're going backwards, examining the characteristics of a sample and making inferences about the populations from which that sample could have reasonably been drawn. In Video 2, we created confidence intervals for the mean and proportion, which are ranges of values likely but not guaranteed to contain the true population parameter. Now, in Video 3, we'll learn how to set up and conduct tests that will allow us to evaluate a claim, suspicion, theory, or hope about a population, when all we know is data about a random sample drawn from the population. We'll cover what hypothesis testing is all about, tests of proportions and tests of means, one-sample tests and two-sample tests, both independent and dependent, test statistics, critical values, and p-values, type 1 and type 2 errors, including alpha and beta. This is a long video, and I work out lots of hypothesis test problems. If you want to bail and not watch the whole video, please use the timestamps to jump to type 1 and type 2 errors before you go. It's an important topic, and I left it until the end. Outline on the left, vocabulary words in yellow. I'm building on the first two videos using color-coded memory aids from them. If anything sounds unfamiliar, please watch the first two videos, linked in the description. I'm going to start with a sample, silly scenario that shows what hypothesis testing does. A high school basketball team shoots free throws poorly. Through the first part of a season, the team only made 58.6% of the free throws they attempted. A sports consultant says he has special socks that will improve the free throw shooting percentage of the team. They wear the socks, shoot a lot of free throws, and make 58.7% of them. The sports consultant claims he's right. Was he? The percentage did go up, but significantly? Hypothesis testing helps us answer the question, could these results have reasonably happened by chance? If the team makes on average 58.6% of their shots, with or without special socks, is it so unlikely that they might shoot 58.7% during a testing period? Do we have convincing evidence that the socks made a difference? Hypothesis testing helps us decide. Here's a definition. A hypothesis is a statement about a population parameter. Usually it's mean mu or proportion p. In hypothesis testing, there are two hypotheses we're considering. One is called the null hypothesis and has the symbol h sub 0, which is often further contracted to h naught, naught being another word for 0. I'll mostly say h naught for null hypothesis. I'll provide examples in just a moment. To start, the null hypothesis is the default assumption or starting point, which usually implies the uninteresting, commonly accepted status quo. You can think of h naught as the dull, boring standard against which a more interesting hypothesis is compared. The more interesting hypothesis is the alternate hypothesis. It can have the symbol h sub a for alternate, and I've seen both upper and lowercase a. It can also have the symbol h sub 1, to contrast it with the sub 0 in the null hypothesis, I suppose, because the null and alternate hypothesis are opposites. In this video, I'll use h sub a for alternate hypothesis. H sub a is based on a more interesting claim, suspicion, theory, hope, or fear. We'll go through lots of examples, and I think this will all make more sense as we go. First, I want you to see where we're going because that can often make the journey more rewarding and less mysterious. Hypothesis testing takes place on a PDF of a sampling distribution. The sampling distribution, remember, is the distribution of all possible sample means. Sample means in the center, near the population mean, are relatively common, and sample means out in the tails are relatively rare. All of our numbers, reasoning, and logic will take place on this diagram. If you can see how everything I explain fits here, you'll have an easy time with hypothesis testing. We'll add information to the PDF as we proceed. But please know, this is the key diagram to understanding everything. Based on the case being analyzed, we'll set up special regions called rejection regions under the PDF out in one or both tails. The nature of the problem will tell us which tails, and we'll get to that soon. Then we take a single sample and calculate its statistic, either the sample mean x bar for a continuous random variable or the sample proportion p hat for a binary success or failure variable. If the sample statistic lies in our predefined rejection region, then we conclude, rightly or wrongly, that the sample could not have reasonably happened by chance if h0 were true, so we reject h0. The underlying assumption is that a sample statistic out here is so unlikely that there must be something else going on, and that h sub a being true is a more likely explanation than h0 being true. On the other hand, if the test statistic does not lie in the rejection region, then we do not reject h0. We conclude that the sample statistic is a reasonable outcome if h0 were true. Earlier, I said hypothesis testing answers a question. Could these results have reasonably happened by chance? And the answer depends on the sample statistic. If it's in the rejection region, then the answer is no. It couldn't have reasonably happened by chance. We conclude that the alternate hypothesis is a more reasonable inference than the null hypothesis. If the sample statistic is not in the rejection region, then the answer is yes, the sample statistic could have reasonably happened by chance. So there's no reason, based on our sample, to abandon h0 in favor of h sub a. h0 is a reasonable inference based on the sample. And that's how hypothesis testing works. Hypothesis testing is a formalized procedure so that researchers across the world can understand, repeat, and validate the findings of others. I'll describe the steps in the procedure next, but I want to spend time on the first step, which can give students troubles. Step 1 is to state the null and alternate hypotheses. The challenge is that we're often dealing with word problems, which can seem difficult to some. As you'll see, the math that comes later is extremely easy, so turning a word problem into a math problem might be the hardest step. I'll go through 3 sample problems. We'll begin each with step 1. A political candidate wants to know if more than 50% of likely voters intend to vote for him. So we first notice this scenario is about the population proportion, P, where P is the proportion of likely voters who intend to vote for the candidate. Problems involving proportions are easy to recognize because you end up counting elements in your sample instead of measuring them. I'll start by drawing the horizontal axis of the sampling distribution PDF upon which we'll conduct the hypothesis test. For proportions, we know the axis represents the proportion P and extends from 0 to 1. When we write our hypothesis, we write h0 followed by a colon, and underneath, h sub a followed by a colon. h0 is usually on top. After the colons are the hypothesis statements about the parameter. Even though the null hypothesis is first in the list, it's often easier to see the alternate hypothesis first based on the wording of the problem. That's the case here. The candidate hopes that p is greater than 0.5. The claim, suspicion, theory, or hope is the alternate hypothesis, so h sub a is p greater than 0.5. This is optional, but on the horizontal axis you can shade in the alternate hypothesis. This makes it easy to identify the null hypothesis, since together they cover the entire axis. So h0 is p less than or equal to 0.5. In later steps, we'll add the rejection region, which is always on the side denoted by the alternate hypothesis. So since h sub a is p greater than 0.5, the rejection region will be out here in the right tail where p is greater than 0.5. When the rejection region is in one tail only, it's called a one-tailed test. By the way, there's nothing special about 0.5. If the candidate wanted to find out if more than 55% of likely voters supported him, h sub a would be p is greater than 0.55, so h0 would be p is less than or equal to 0.55. Still a one-tailed test with the rejection region in the right tail. Now the second problem. Step 1. State the null and alternate hypotheses. A manufacturing process takes an average of 30 minutes. An engineer claims to have designed a tool that can reduce the average process time. Test the engineer's claim. The interesting claim is that the process time can be less than 30 minutes compared to the accepted standard of 30 minutes. H sub A is mu less than 30.0 minutes. We use mean mu instead of proportion p on the axis because minutes is a continuous random variable. H naught fills the rest of the horizontal axis, so mu greater than or equal to 30 minutes. The test is a one-tailed test with a rejection region out on the left side towards the direction of the alternate hypothesis, mu is less than 30 minutes. Problem 3. We're stating the hypotheses. A company sells 40-pound bags of corn for animal feed. The company president wants to make sure the average weight isn't drifting away from 40 pounds. If the bags are too heavy, the company is wasting money putting in extra corn. If the bags are too light, the customers will complain. Do the bags still truly weigh 40 pounds? Here's our horizontal axis with parameter mu in pounds. The interesting suspicion is that mu is not equal to 40 pounds. Heavier or lighter, we don't know. We want to test for either. Since H sub A is mu not equal to 40 pounds, that only leaves 1 point on the horizontal axis for H naught. H naught is mu equals 40 pounds. Since H sub A is not equal to, it has two directions. We'll have a rejection region in both tails, so this is a two-tailed test. If our sample statistic is in either rejection region, we'll reject H naught and conclude that the population mean is not 40 pounds. Be on the lookout for wording in the problem that indicates a direction, so you'll know if H sub A should be less than, greater than, or not equal to. These correspond to left-tailed, right-tailed, and two-tailed rejection regions, respectively. Those are the sample problems. As we cover each step in the hypothesis testing procedure, we'll apply it to these three problems one at a time. But first, a trick question. If the alternate hypothesis, H sub A, is x bar greater than 20, what's the null hypothesis? Since H naught covers all possibilities not covered by H sub A, it's tempting to say H naught is x bar less than or equal to 20. But it's a trick question, because hypotheses are always statements about population parameters, like mu and p, never about sample statistics, like x bar or p hat. Don't be fooled, and be sure to always use parameters in your hypothesis statements. Step 2 is to state the significance level, which is a low probability representing the threshold of likelihood against which we'll compare or test the likelihood of the sample statistic. The most common values are 0.05, 0.02, or 0.01. Since they're probabilities, I'll make them yellow to match our memory aid colors. On the sampling distribution PDF, it's the area or probability of the rejection region here. The significance level has the symbol alpha, so we can label the rejection region as alpha. In video 1, I said the significance level was 1 minus the confidence level, and as you can see, common alpha values of 0.05, 0.02, and 0.01 correspond to common confidence levels of 0.95, 0.98, and 0.99. In a problem statement, you'll be given alpha like this. Test the hypothesis at a 0.05 level of significance, or test the researcher's claim with alpha equals 0.01. Alpha can be in decimals or a percent. It's possible that you might be given a confidence level instead, in which case alpha is 1 minus the confidence level. For our 3 sample problems, I'll just choose the alpha levels. 0.02 for the politician, we already stated the hypotheses in step 1. 0.01 for the manufacturing process, and 0.05 for the feed bags. The third step in hypothesis testing is to identify and evaluate the test statistic, which will be a z-score or t-score. It's the score of the sample statistic p hat or x bar, which is the number of standard errors that is from the hypothesized parameter. In previous videos, these scores were blue, so we'll continue with that memory aid. Here's the general formula for the test statistic. This should be a review from other videos. In step 3, we need to decide if we're using a Z or T statistic. This is the same as stating whether our test statistic has a normal Z distribution or a student's T distribution. It's Z if both of these are true. We must know the population standard deviation sigma, and the sampling distribution must be approximately normal. As I demonstrated in video 1, continuous random variables have a sampling distribution that's approximately normal if the sample size is at least 30. And for binary success or failure attributes that we use for proportions, I demonstrated in video 2 that the sampling distribution is approximately normal as long as both np hat and nq hat are greater than or equal to 10. If we cannot say yes to both of these, then we must use a t-distribution, and our test statistic will be a t-score. Our populations can consist of either continuous random variables, attributes we measure, or binary variables that we call success or failure in statistics that we count to calculate proportions. For both types of attributes, we either know the population standard deviation sigma or we don't. In this case, where we know sigma for continuous random variables, the test statistic for x bar is z equals x bar minus mu divided by sigma over the square root of n. This is how many standard errors x bar is from the mean. In the case where we don't know sigma for continuous random variables, the test statistic is t equals x bar minus mu divided by s over the square root of n. We'll use the sample standard deviation s as an imperfect estimator for sigma, so we use the looser t-distribution to account for the extra uncertainty. For proportions where sigma is known, the test statistic for p hat is z equals p hat minus the population proportion p divided by sigma over the square root of n. It's the same formula as for continuous random variables, with p hat in place of x bar and population proportion p in place of population mean mu. For proportions where sigma is not known, the test statistic for p hat is z equals p hat minus p divided by the square root of pq over n. Because the square root of pq is a good unbiased estimator of sigma, there's no extra uncertainty to account for, so we can use the tighter z-curve instead of the looser t-curve. And the situation in real life outside of school is that the top row just never happens. We don't ever really know sigma, so these are the formulas for the test statistics. And it's easy to get confused because you might think t means continuous random variable, but actually t means you don't know sigma and you have to use a biased estimator, which happens to be the case for continuous random variables. And over here, it sure looks like z means proportion, but z actually means you either know sigma or you have a good unbiased estimator, which happens to be the case for proportions. It wouldn't be too unlikely in your class or textbook to be given a problem that includes a phrase such as, based on past history, researchers know the population standard deviation sigma is 1.4 millimeters, or the engineer who designed the machine states the standard deviation is 0.08 seconds. Then you'd know sigma and could proceed with the normal z-distribution. These are contrived problems, but that's okay. Your instructor wants to teach you how to solve the problems with z-scores, and that's often taught before the t-distribution, so it all has a purpose in school. But of course, in actuality, researchers have no idea if the standard deviation changes over time, and believe me, the engineer doesn't know the standard deviation of her machine's processing time. But be on the lookout to use z for continuous random variables in school if you're given sigma or sigma squared. Okay, sorry for that mini lecture, but step 3 is to calculate the test statistic. So of course, we need to first decide z or t. Continuous random variables will usually get t-test statistics, and as long as the sample size is large enough, proportions will usually get z-test statistics. Before we do step 3 for our 3 sample problems, sorry for these delays, there's a lot to cover with test statistics. Let's take this opportunity to label some key features of the sampling distribution PDF where our work takes place. All the math we do will have an interpretation on the PDF, so it's a great tool for learning and remembering. For every hypothesis test you conduct, you should draw a PDF. I'll use sample problem 2 to annotate the PDF. The unit of measure for our random variable is minutes, so I'll label the horizontal axis minutes. The mean of the sampling distribution is the value mentioned in the null hypothesis. While conducting hypothesis tests, we always assume the null hypothesis H0 is true. H0 will always have the form mu less than or equal to some x, mu greater than or equal to some x, or mu equal to some x. Whatever x is, that's our assumption for the population mean mu, and hence the mean for the sampling distribution mu sub x bar. We can add a 0 subscript to mu to get mu naught. The naught should remind us of H naught, the null hypothesis, because that's where the value for mu naught comes from. For this example, mu naught is 30 minutes. For proportions, the hypothesized mean is p naught, the proportion mentioned in the null hypothesis. Alpha is the total area or probability in the rejection regions. This is a left-tailed test since the alternate hypothesis H sub A is mu is less than 30. Alpha is 0.01, so this area is 1% of the total area under the curve, leaving 99% unshaded. There's a point on the horizontal axis right here at the boundary that separates the regions of rejection and non-rejection. We can call that the boundary point, but it doesn't have an official name because we refer to that boundary point by alpha or by its blue score, we'll mention next. As a reminder, every point under the PDF is a certain number of standard errors away from the mean mu naught. The standard error is the actual or estimated standard deviation of the sampling distribution. The memory aid color for standard error is pink. So naturally, the boundary point has a blue t-score, and it's called the critical value. Critical value should sound familiar from video 2. When we constructed confidence intervals, the critical value was the blue number of standard errors corresponding to the boundary of the confidence interval. In hypothesis testing, it's the blue number of standard errors corresponding to the boundary of the rejection region. So the boundary point has two interesting color-coded attributes: the blue t-score, critical value, and the yellow probability, beyond alpha. Another important point on the PDF is the sample statistic x bar, or p hat for proportions. The memory aid color for the sample statistic is red. Its actual location will depend on the sample we draw. I'll just put it here. The sample statistic has the same two interesting color-coded attributes. Its blue t-score is called the test statistic, so the test statistic is the blue t-score of the red sample statistic. And the yellow probability out beyond the sample statistic is called the p-value. The p-value gives us an indicator as to the likelihood of observing our sample statistic, assuming the null hypothesis is true. A larger p-value denotes a more likely test statistic, closer to mu naught, than a smaller p-value. We'll cover all the details later, but everything labeled on this diagram should make sense to you. Let me show a simpler, cleaned-up version of this screen. I'll remove the boundary threshold value because when we refer to the boundary, we use alpha or the critical value. Everything we'll say and every number we'll use has a meaning and interpretation on this diagram. Please make sure you know what everything means. The sample statistic, p-value, and test statistic all describe the value x bar. Alpha and the critical value describe the boundary point. As I've said, this diagram is the key to understanding hypothesis testing, and seeing or sketching this will make everything simple. Pause and take a screenshot. Now take a screenshot or sketch it out yourself. You should be able to explain every label to an interested high school freshman. Okay, at long last, let's do step 3 for each of our 3 sample problems. Calculate the test statistic. Our first example was about the political candidate. This is a test of proportions, so the test statistic will be a z-score, since our estimate of sigma is the unbiased square root of pq. We do need to check that our sample size is large enough, meaning NP and NQ are both greater than or equal to 10. We'll do that when we get to our sample data. We already know some numbers, so let's sketch out our PDF. The mean of the sampling distribution, P0, is the hypothesized proportion mentioned in H0, which is 0.5. For the rejection region, the alternate hypothesis has greater than. The rejection region is one-tailed on the right side. We can label it alpha. Okay, that's a good start. Here's the formula for the test statistic, the distance in standard errors between P hat and P0. Well, we need P hat, and that comes from our sample data. We pulled 400 likely voters. 224 intend to vote for the candidate. Let's check that NP and NQ are both greater than or equal to 10. You may recall that NP hat is the number of successes in the sample. Well, that's 224 right here, clearly greater than or equal to 10. But remember, when doing math for hypothesis testing, we always assume H0 is true. So instead of NP hat and NQ hat, we're going to use NP0 and NQ0. P0 is 0.5, and we get that number from H0. Since Q0 is 1 minus P0, Q0 is also 0.5. N is 400, so our checks both become 400 times 0.5 greater than or equal to 10. 200 is greater than 10, so the sample size is large enough that the binomial distribution will closely match the normal, so it's okay to use z-scores. Okay, back to the test statistic formula. We need P hat. P hat equals x over n, where x is the number of successes, 224, and n is the sample size. 224 divided by 400 equals 0.56, and that's P hat. Let's add that to our PDF. We don't yet know if it's in the rejection region. We'll figure that out later. So for now, we'll just put it here. Okay, we know the numerator of the test statistic because we know both P hat and P0. The denominator is the standard error. For proportions, it's the square root of PQ over N. Now, for confidence intervals, we used P hat and Q hat because that's all we had. Again, for hypothesis testing, when we do our math, we always assume H0 is true. So we'll use P0 and Q0. We know all the variables, so we can calculate Z. The test statistic is Z equals 0.56 minus 0.5 divided by the square root of 0.5 times 0.5 divided by 400. This turns out to be 2.4, and that's step 3, calculating the blue test statistic, Z-score, that corresponds to the red statistic, P hat. For the manufacturing process problem, the process is run 35 times with the new tool. The average time to complete the process for these runs was 29.1 minutes, with a sample standard deviation S of 2.45 minutes. We don't know the standard deviation of the sampling distribution, sigma sub x bar, so we'll have to calculate an estimate using the standard deviation of the sample, S. This means we'll need to use a t-statistic instead of z due to the uncertainty in estimating sigma sub x bar. Let's mark up a sampling distribution PDF with what we know. The mean of the PDF will be the hypothesized mean of the population, 30.0 minutes. The alternate hypothesis has less than, so it's a left-tailed test with the rejection region here, whose probability is alpha. The sample statistic x bar is 29.1 minutes. We're not sure yet where this is in relation to the rejection region, but it's less than 30, so we'll put it here. The formula for the test statistic t is x bar minus mu naught divided by the sample standard deviation over the square root of the sample size n. S divided by the square root of n is the standard error of the mean, our biased estimate of the standard deviation of the sampling distribution. So the test statistic t turns out to be negative 2.173. X bar is 2.173 standard errors below the mean mu naught. For the 40-pound bags of corn, 200 bags were weighed, and the average weight was 39.976 pounds, with a sample standard deviation of 0.122 pounds. As usual, we don't know sigma, so we'll use t as our test statistic. Let's sketch the PDF. This alternate hypothesis is not equal to, so that means a two-tailed test. Since the area of the rejection regions equals alpha and the tails are symmetrical, we can put alpha over 2 in each tail. And x bar is less than mu naught, so we'll put it here in the left half. Here's the formula for the test statistic t. We know all the variable values, so we get t equals 39.976 minus 40 divided by 0.122 over the square root of 200. This turns out to be t equals negative 2.782. The red sample statistic x bar is 2.782 standard errors below the mean. The fourth step is to compare the likelihood of our test statistic to the stated significance level alpha. In other words, is the test statistic in the rejection region? Well, this isn't quite as simple as it sounds. Alpha is a yellow probability, and our test statistic is a blue score. They both correspond to points on the horizontal axis, and we need to find out where these points are relative to each other to decide if the test statistic is in the rejection region. But we can't compare these numbers directly. Using our z and t tables, we know how to convert back and forth between probabilities and scores, so we have a choice. We can convert the probability alpha to the corresponding blue critical value here and compare that to the blue test statistic since they're both scores. Or we can find the yellow probability associated with the test statistic, the p-value, and compare that to alpha since they're both probabilities. The choice will always yield the same result. You'll probably never be told which method to use. You're just expected to perform the test, so it's up to you. It's not too terribly important, but the two alternatives have names corresponding to the conversion we make. When we determine the critical value corresponding to alpha to compare blue scores, that's called the critical value method. When we determine the p-value of the test statistic to compare yellow probabilities, that's called the p-value method. I'll do step 4 for our 3 sample problems using both methods, and you'll see how easy they are. When you're conducting hypothesis tests in exams or homework, just use one method. There's no need to do it twice, but I'll do these both ways so you can see. The critical value method seems a little more straightforward to me, but you might have a different preference. After we conduct these first 3 hypothesis tests both ways, I'll do the remaining example problems using the critical value method. For the political candidate problem, we had alpha equals 0.02, and the test statistic z equals 2.4. Remember, the test statistic is the z-score of p hat, the sample proportion. Let's find the blue critical value of the boundary point. Since we want to get a blue score from the z table, we need to look up a yellow probability. The probabilities in the table are to the left of the score, that is, the probability up to z. The rejection region to the right of the boundary point is 0.02, so the probability to the left is 0.98. We look up yellow 0.98 in the body of the table. It looks like 0.9798 is the closest, and that probability corresponds to a z-score of 2.05. So the z-score at the rejection region boundary, the critical value, is 2.05. Here's the test statistic, 2.4, that we calculated in step 3. When we put it on the PDF, we didn't know exactly where it belonged. Now we can see that it's out beyond the critical value. The result of step 4 is that the test statistic is in the rejection region. We're going to reject the null hypothesis, but that will be step 5. Okay, we did step 4 using the critical value method. Now let's use the p-value method. We need to find the p-value corresponding to the test statistic, 2.4, and compare that to alpha. We look up blue 2.40 in the margins of the z-table to get a probability of 0.9918. This means the probability of a random z-score being less than 2.4 is 0.9918. This gives us the probability up to z equals 2.4, but the p-value is the probability out beyond 2.4 in the direction of the null hypothesis. So we subtract 0.9918 from 1 to get the p-value of 0.0082. This is a very small probability, smaller than alpha, so the test statistic must be beyond the boundary in order to mark out a probability smaller than alpha. Of course, both methods yield the same results. They both showed that the test statistic is in the rejection region. The p-value method has a straightforward interpretation. You can think of the p-value as representing the likelihood of the sample statistic, and alpha is the cutoff. If the test statistic is less likely than alpha, we reject the null hypothesis. This is true for tests in either or both tails. If p-value is less than alpha, reject H0. For the critical value method, there isn't a simple rule to memorize that works for both tails, because in the left tail we reject if the test statistic is less than the critical value, but in the right tail we reject if the test statistic is greater than the critical value. So don't rely on rules or your memory. Rather, draw a PDF and rely on your understanding to just figure out if the test statistic is in the rejection region. And that's all there is to step 4. Sample problem 2, the manufacturing process. Let's start with the critical value method again. In step 3, we decided this was a t-statistic, so we need to find the t-score corresponding to the boundary here, the critical value. T-tables come in different types. Many are similar to z-tables in that they have positive scores and probabilities on the right half of the PDF. So let's take advantage of the symmetrical nature of the bell-shaped PDF and, temporarily, flip it around so we can use our table to find the positive t-score. Since alpha is 0.01, the remaining area must be 0.99. So let's look up the t-score having 99% probability to its left. The sample size is 35, so the degrees of freedom is 34. We get 2.441, which is the t-score over on the right side. Remember, we flipped the PDF around so we could use the t-table to find this t-score. When we flip it back around, the t-score is negated to negative 2.441. So the critical value, marking the boundary of the rejection region, is negative 2.441, and our test statistic from our sample is negative 2.173 here. Since the test statistic is not in the rejection region, the test fails to reject H0, which we'll do in step 5. Now let's use the p-value method. We should get the same answer. So we want to compare yellow probabilities. We already have alpha, the probability in the rejection region, and we need to find the probability associated with the test statistic, negative 2.173, the probability out beyond negative 2.173 in the direction of the alternate hypothesis. Now, as I've drawn this, the p-value obviously looks much larger than alpha, but that's just because I sketched the test statistic here. When we conduct the hypothesis test, we won't really know where the test statistic lies relative to alpha's boundary. Not until we're done with the test. The p-value could be larger or smaller than alpha. That's what we're about to find out. Again, our statistics are here in the left tail, but t-tables usually deal only with the right side. This makes sense because everything is perfectly symmetrical. You only need one of the halves. We'll flip the PDF around again and find the probability up to positive 2.173, which will be the probability in the orange region. In our t-table, we're on the row with 34 degrees of freedom. We read across until we find the blue value closest to our blue target score of 2.173. It looks like we're between 2.136 and 2.441, but definitely closer to 2.136. So our probability is closer to 0.98 than 0.99. This range can cause confusion when using t-tables, which is why I slightly prefer the critical value method. But you can use a calculator to find the precise t-score, which is 0.9816. Obviously, I'm not covering calculator techniques in these videos. 0.98 is close enough to suit our purposes, so we'll call the orange area 0.98. This makes the p-value 0.02. Well, we have the p-value, so we don't really need to spin the PDF back around. But here it is in context. The p-value is a higher probability, more likely, than alpha, so we won't reject H0. As we expect, the critical value method and p-value method yield the same test results. The third example is the company that sells bags of feed. Yellow alpha equals 0.05, and in step 3, we found the blue test statistic was t equals negative 2.782. Of course, we can't compare them directly. For the critical value method, we'll compare blue scores, and for the p-value method, we'll compare yellow probabilities. For the critical value method, we'll find the critical value associated with alpha. Since this is a two-tailed test, we put half of alpha in each tail. Alpha is 0.05, so 0.025 goes into each tail. Here are the critical values at the boundaries of the rejection regions. Due to symmetry, these critical values will have the same magnitude, but the one on the left will be negative. Using a t-table, it's easy to find this positive value that corresponds to a cumulative probability of this area, 0.975. The sample size was 200, so degrees of freedom equals 199. But when we go to a t-table, we're not likely to find a row for 199 degrees of freedom. When the degrees of freedom get this high, t-values in each probability column change very little, so we're safe to use the 200 row. 200 degrees of freedom with a probability of 0.975 yields a critical value of 1.972. So the critical value on the right side is positive 1.972, and on the left side it's negative 1.972. Our sample statistics test statistic is negative 2.782, and we can now see that in actuality it's out beyond the critical value. The test statistic is more extreme than the critical value, so it's in the rejection region. In step 5, we'll reject H0. As promised, let's do step 4 with the p-value method. We need to find the p-value associated with our test statistic, negative 2.782. As usual, when the action is in the left half of the PDF, we'll have an easier time flipping the diagram around. We want this probability, so we'll use our t-table to find the probability up to here, then subtract that from 1 to get the p-value. We'll use the 200 degrees of freedom row and search across to find the number closest to 2.782. And we never find one. 2.782 is off the charts, meaning the probability of a t-score up to 2.782 is greater than 0.995. Subtracting that from 1 means the p-value is less than 0.005. Let's flip the PDF back around and put our p-value and the test statistic more to scale compared to alpha over 2. For a two-tailed test, we compare the p-value to alpha over 2. Just draw a PDF and you don't have to remember. It's right here. The p-value of our test statistic, 0.005, corresponds to a smaller probability than alpha. So x bar must be out further than the boundary, in the rejection region, so we'll reject H0 in step 5. In each example problem, the two methods yielded the same results. This is expected, of course. Both methods answer the same question: is the sample statistic in the rejection region? The critical value method does it by comparing blues, the test statistic to critical value. The p-value method does it by comparing yellows, p-value to alpha. The last step is to state the results of our hypothesis test. In video 2, the statement of our confidence intervals followed a pattern and included several key components. The same is true with hypothesis test conclusions. For the first example, with the political poll, we rejected H0. Here's a good summary of our findings. We reject the null hypothesis at a 0.02 significance level. Our sample provides significant evidence that the proportion of likely voters who intend to vote for the candidate is greater than 0.5. Each conclusion includes a statement that clearly rejects or fails to reject the null hypothesis and states the significance level alpha at which the test was conducted. Then another sentence that restates the conclusion using the language of the alternate hypothesis. The sample either did or did not provide significant evidence, then restate the alternate hypothesis in plain language. You can think of the first sentence as the summary headline and the second sentence as a contextual explanation of the findings. If we had reached the opposite conclusion for this problem, we fail to reject the null hypothesis at a 0.02 significance level. Our sample does not provide significant evidence that the proportion of likely voters who intend to vote for the candidate is greater than 0.5. These sentences have the same components. Let's state the conclusion for sample problem number 2, the manufacturing process. The sample statistic was not in the rejection region, so We failed to reject the null hypothesis at the 0.01 significance level. The sample did not provide significant evidence that the engineer's new tool design reduced the average processing time to less than 30.0 minutes. For problem number 3, the test statistic was in the rejection region, so we reject the null hypothesis at a significance level of 0.05. The sample provides significant evidence that the bags of corn have an average weight that is not equal to 40 pounds. Please pay attention to this wording. You should always include in your conclusion statement the results in terms of the alternate hypothesis. Since the alternate hypothesis is mu not equal to 40 pounds, our conclusion should state not equal to 40 pounds. But we do know that our sample was in the rejection region in the left tail, since our test statistic was negative. So you may, check with your instructor, add a sentence. The evidence suggests that the average weight is less than 40 pounds. Don't include the sentence instead of the one that matches the alternate hypothesis. For two-tailed hypothesis tests where H0 is rejected, either include sentence 3 or not, but always include the first two sentences. Now let's do a problem step by step, uninterrupted, from start to finish. A company makes baseball bats. Its most profitable model must weigh on average 30.2 ounces before finishing and staining. Set up a hypothesis test at the 0.02 significance level to see if the average weight has drifted away from 30.2 ounces. Step 1 is to state the hypotheses. The parameter will probably be either mu for means or p for proportions. This problem statement is about means, so the parameter in the hypothesis statement will be mu. It's often easiest to see the alternate hypothesis first. It's the claim, suspicion, theory, hope, or fear expressed in the problem statement. Here, it's that mu is no longer 30.2 ounces. The suspicion doesn't have a direction, so it's a two-tailed test, and H sub A is mu not equal to 30.2 ounces. This means H0 is mu equals 30.2 ounces. Step 2 is straightforward. We were given alpha equals 0.02. Step 1 and 2 can be done without knowing the sample data. Let's set up the sketch of our PDF. We'll add to it as we go. Remember, the PDF is the sampling distribution of all samples we'd get if H0 were true. The mean mu0 we get from H0, 30.2. It's a two-tailed test because H sub A has not equal to, so we put half of alpha in each tail. Since alpha equals 0.02, half of alpha is 0.01. Step 3 is to find the test statistic, which is the blue t-score of the red sample statistic x bar. So now we need sample data. The sample is 25 bats whose average weight x bar is 30.23 ounces. The standard deviation of the sample, S, is 0.084 ounces. So on our PDF, x bar is greater than mu0, but we don't know yet if it's in the rejection region. But it's on the right side, so let's put it here for now so we're not cramped. For step 3, what kind of score will we use, Z or T? This is a test of means, and we're not told anything about the population variance or standard deviation. Since we'll estimate the sampling distribution standard deviation, pink sigma sub x bar, we'll use a t-distribution. So we need to find the t-score of our sample statistic x bar. Here's the formula. X bar minus mu0 divided by S over the square root of n. The numerator is x bar's distance from the mean. The denominator is our biased estimate of the PDF's standard deviation. So t tells us x bar's number of standard errors from the mean. We know all four of these numbers, so it's simple to get 1.786. Step 4 is to make the comparison. Is the test statistic in the rejection region? When we plotted x bar, we put it here in the non-rejection region. Since x bar is greater than mu0, we knew it was in the right half of the PDF, but we didn't know where. Maybe it's out here in the rejection region. Step 4 is where we find out. We need to find the critical value, which is the t-score of this boundary point where alpha begins. We need to use a t-table to convert a yellow probability to a blue standard score. The probability we'll look up is the cumulative probability up to the critical value, 0.98 in the middle plus the left tail, probability 0.99. Degrees of freedom is 24, which is the sample size minus 1. We get 2.492. The test statistic is closer to the mean, not out in the rejection region. We failed to reject the null hypothesis at the 0.02 significance level. The sample did not provide significant evidence that the average weight of the baseball bats was different than 30.2 ounces. So let's put this in context. The sample mean was 30.23 ounces, which is heavier than the hypothesized value of 30.2 ounces. But our hypothesis test concluded that if the true population mean was 30.2 ounces, a sample size 25 having a mean of 30.23 could have reasonably happened by chance. The sample doesn't provide significant evidence to reject H0. When the test statistic is in the rejection region, we conclude that the sample mean was not likely to have happened by chance if H0 were true. So we conclude that H0 must not be true and reject it. Okay, one more at normal speed. A service station claims that customers wait on average no longer than 20 minutes for an oil change. A skeptical consumer advocacy group thinks the wait is longer. They randomly sample 50 oil changes and find that the average wait time was 20.65 minutes, with a standard deviation of 2.77 minutes. Using this data, test the company's claim at a significance level 0.05 that the average wait time is no longer than 20 minutes. For step 1, we need to be careful because the word claim appears in the problem statement, and that's one of our clue words, claim, suspicion, theory, hope, or fear, that describe the alternate hypothesis. But the consumer advocacy group has a suspicion that's challenging the status quo. Their suspicion is that mu0 is greater than 20 minutes. That's the alternate hypothesis. So the null hypothesis covers everything else, mu0 less than or equal to 20 minutes. For step 2, we're given that alpha is 0.05. Here's the sampling distribution PDF. It's a right-tailed test since H sub A says greater than. Alpha is 0.05 and mu0 is 20 minutes. For step 3, we're testing means and we're not given the population standard deviation sigma. So we'll use a t-statistic. The problem statement gives us the sample statistic and x bar equals 20.65 minutes. That's greater than mu0, so we'll plot it in the right half of the PDF. We don't know yet if it's in the rejection region. The rejection region boundary is right here. We need to find the critical value of this point. Alpha is 0.05 to the right, so the cumulative probability up to the critical value is 0.95. Degrees of freedom is 49. When degrees of freedom get up this high, you'll usually have to use the closest match. The critical value at 50 degrees of freedom is 1.676. It won't be any less than this because the chart shows t-values increasing as degrees of freedom decreases. So the score at 49 is at least 1.676. So the critical value is 1.676 and the test statistic is 1.659. Wow, this one was pretty close, but the test statistic is barely in the region of non-rejection. We failed to reject the null hypothesis at a 0.05 significance level. The sample does not provide significant evidence that the average wait time for an oil change is greater than 20 minutes. All the tests we've done have been one-sample hypothesis tests. We draw one sample and, by conducting a hypothesis test, compare the results to a commonly accepted null hypothesis. But more common, and I think more interesting and perhaps more useful, are two-sample hypothesis tests where we have two populations we want to compare. We draw a sample from each, so two samples. The main idea, PDF concept, and math are all the same. Please don't be alarmed, but there are two types of two-sample tests, two dependent samples and two independent samples. And don't be alarmed again, but there are two scenarios for independent samples. We'll cover it all and make it clear. First, let's talk about dependent samples. With dependent samples, each member of one sample is linked to exactly one member of the other. A common dependent sample scenario is a before and after study, where we take a sample measurement before and after some treatment. For example, to test the effectiveness of a memory enhancement training course, 16 people are randomly chosen and given a memory test, and their scores are recorded. This is called a pretest, evaluating the subjects before the treatment is applied. The 16 pretest scores are represented by the green circles. Then the subjects attend a training course intended to improve their memories. After a week, they each take another memory test and their scores are recorded, orange circles. So we have 16 pairs of observations, a before and after score for each of the 16 people. We want to know, was the training course effective? In other words, is there a difference between the sample statistics? This will be the first two-sample hypothesis we'll test, but I want to talk a bit more about dependent and independent samples first. The purpose of dependent samples is to reduce extraneous random fluctuations between the two sample groups, so that any differences we observe can be attributed to the treatment we're trying to evaluate. Can you see how before and after dependent samples is a more effective evaluation than testing 16 random people who haven't had the training and comparing those scores to 16 different random people who have? The two groups could be very different, and there's no way to attribute any difference in test scores we observe between the groups to the effectiveness of the memory training. By using the same 16 people, we eliminate or reduce the effect of other random fluctuations on our study. Any difference is more likely the result of the memory training. Before and after studies are a very common two-dependent sample scenario, but not the only one. We can also identify or create two similar corresponding groups and give each group a different treatment. For example, to test the effectiveness of two fertilizers, we may set up pairs of flower pots, each with identical soil composition, water, and sunshine, differing only in the fertilizer being tested. This has the same effect of limiting, as much as possible, unknown variability between groups, so that any variability we observe can be more readily attributed to the treatments being tested. That's the idea with dependent samples. Researchers often try to use twins to conduct dependent sample tests. Observed differences are more likely to be attributed to the treatments applied rather than to inherent differences between the people, since the people, being twins, are so similar to start with. Dependent samples are sometimes called paired samples or matched samples. Dependent sample tests are common and useful. When conducting a two-sample hypothesis test, the null hypothesis is that there's no difference between the groups. If we observe significant evidence that the scores increased after the training, then we'll reject the null hypothesis and conclude that the treatment caused a difference, but H0 is always no difference. If there's not a natural link between pairs of observations in the two samples, then the samples are independent. Independent samples are drawn from two distinct, unrelated populations. I'll represent independent samples as disjointed sets of green and orange circles to emphasize their independence from each other. For example, we may want to compare attributes of smokers and non-smokers, or men and women, or freshmen and seniors. We want to compare two different populations, so we simply draw a random sample from each. There's no link or connection between members of the different samples, and the samples don't even have to be the same size. Independent samples come up a lot to compare different groups of people, different medicines, different treatments, different processes or procedures, different machines, and so on. Independent sample tests are also common and useful. Let's see how to perform tests on dependent samples by testing the memory training claim. We'll test at the 0.05 level of significance. Here's the memory aid for dependent samples, pairs of linked or matched observations. Here are the 16 scores from the pretest before the memory training. And here are the 16 corresponding scores a week after the training. And here are the differences. The only thing you need to know about two dependent sample tests is that we treat them exactly like one sample tests, where the differences are the random variables. That's it. The average of these differences, x bar sub diff, is 1.53. It's very common to use the diff or d subscript to mean difference. The standard deviation of the differences, s sub diff, is 3.37, and the sample size n is 16. Step 1. As I stated earlier, the null hypothesis for two-sample tests is almost always that there's no difference between the groups. The interesting claim is that memory scores will increase, that mu sub diff, the average score difference, is greater than 0. So the null hypothesis is that mu diff includes 0. And by convention, h0 also covers the rest of the horizontal axis, so mu diff less than or equal to 0. We're given alpha equals 0.05, and h sub a tells us that this is a right-tailed test, so alpha over here. The test statistic t is 1.53 minus 0 divided by 3.37 over the square root of 16. This is 1.816. The critical value is the t-score corresponding to 0.95 and 15 degrees of freedom, which is 1.753. The test statistic is in the region of rejection, so we reject h0. We reject the null hypothesis at the 0.05 significance level. The sample data provides significant evidence that the memory test scores increased after the memory training program. The takeaway is that two-sample tests, where the samples are dependent, are conducted exactly like one-sample tests, where the random variable is the difference between each corresponding pair. Now, I want to build a chart for you, but first, let me show you why. Here's a simple formula we're already familiar with, the t-statistic for a one-sample test of means. The test statistic t equals x bar minus mu naught divided by the sample standard deviation s over the square root of the sample size n. The degrees of freedom is n minus 1. Here's the general test statistic formula. The test statistic is the sample statistic minus the hypothesized parameter divided by the standard error. The degrees of freedom is some function of the sample size. The sample statistic is always easy to determine, and the hypothesized parameter always comes straight from h0. But the formula for pink standard error can be different depending on the type of test. For example, we've already seen two formulas, s over square root of n for means, and the square root of p hat times q hat over n for proportions. For two-sample tests, there are more, and for t-tests, the formula for degrees of freedom are different. Remember, we need degrees of freedom to find the critical value for t-tests. So I want to make a chart showing standard error and degrees of freedom formulas, and for completeness, we'll start with the one-sample tests we've already covered. For means tests, if we know sigma, then we'll conduct a z-test, and the standard error will be sigma divided by the square root of the sample size n. Since we know sigma, we use it to find the standard deviation of the sampling distribution, the standard error. We just need to be able to assume that the sampling distribution is normal, which is a good assumption if the sample size n is greater than or equal to 30. If we don't know sigma, then we estimate it with our sample standard deviation s. This is a biased estimator of the population standard deviation sigma, so we must use a t-test. Our best guess at the standard deviation of the sampling distribution is the standard error, which is s divided by the square root of sample size n. For t-tests, we must also know the degrees of freedom. For one-sample t-tests, it's n minus 1. For a one-sample test of proportions, we can conduct a z-test as long as there are at least 10 successes and 10 failures in our sample. See video 2. The standard error is the square root of p hat times q hat over n. This is an unbiased estimator of the population standard deviation sigma, so we can use a z-test. The topmost alternative is rare in real life, since sigma is almost never known. For two-sample tests, let's start with dependent samples. Here's our memory aid diagram. These samples are often called paired or matched samples. As we've seen from the memory training example, these tests are just like one-sample tests, with the same formulas for standard error and degrees of freedom. That leaves two independent sample tests. Here's the memory aid diagram. Two distinct samples from two completely different independent populations. Again, we have tests of means and tests of proportions. For means tests, there are two scenarios. One where we have some reason to believe that the green and orange populations we're comparing have the same standard deviation, and the other where we don't make this assumption. For the first scenario, it's possible to have a reason to assume the two sigmas are the same, even if we don't actually know what sigma is. This is an uncommon assumption and is based on prior knowledge and experience from sampling the populations. I've said before that knowing sigma hardly ever happens, but assuming two sigmas are the same, even if we don't know the value, can happen. Possible, but uncommon. In the unlikely case where we do know sigma, then as long as the sampling distribution is approximately normal, if both sample sizes are greater than or equal to 30, then we can use a z-test. The numerator of the standard error is equal to sigma, which we claim to know. For the denominator, it's easy to remember that for a one-sample test, the standard error is sigma, or s, divided by the square root of n. For a two-sample test, the denominator is the square root of both sample sizes, n1 plus n2. Super easy, but of course, we hardly ever truly know sigma. More likely is the case where we don't know sigma, even though we're assuming it's the same for both populations. The idea is that we're going to pool the two sample variances to get a better estimate of their shared true standard deviation sigma. Each sample has its own sample standard deviation S, green and orange. Remember, these are both independent estimators of the common population standard deviation sigma. Due to random variability between samples, these two sample standard deviations, or variances, aren't likely to be equal to each other, or equal to sigma, even though sigma is supposed to be the standard deviation of both populations. So to get a better estimate of sigma, we pool the sample variances by taking their weighted average. S squared subpooled, or sub p, is the common symbol to denote the pooled variance. The only reason we're pooling our samples is because we're assuming the population standard deviations have the same sigma. So we pool the variances to get a better estimate of sigma than either independent sample alone. In the other scenario over here, where we're not assuming the populations have the same variance or standard deviations, we won't pool the samples. Here's the formula for the pooled variance. It might look intimidating, but the numerator is each sample variance weighted by its degrees of freedom, and the denominator is the sum of the weights. n1 minus 1 plus n2 minus 1 is n1 plus n2 minus 2. This is the pooled variance with units squared. So to get back to the random variable units, not squared, we take the square root of the pooled variance to get the pooled standard deviation. Okay, we're almost there. We have the estimated pooled population standard deviation S sub p, but we want the pink standard error, which, as usual, has the form standard deviation divided by square root of sample size. Here's the formula for standard error based on the pooled standard deviation. S sub p is the pooled standard deviation whose formula we just covered. The right factor is how we divide by the square root of the sample size. Since there are two samples, there are two sample sizes. We add the reciprocals of the two sample sizes and take the square root. The degrees of freedom is the sum of the degrees of freedom for the two samples, n1 plus n2 minus 2. We'll do examples after we finish the chart. Tests of proportions don't ever have assumptions pertaining to whether their variances are equal. Since the variance of a binomial distribution is npq, assuming that the variances are equal is the same as assuming the proportions are equal, which is what we're testing for in the first place. So two-sample tests of proportions are all the same. They're z-tests, not t-tests, because the standard error formula we'll show in a second is an unbiased estimator of the standard deviation of the sampling distribution. We just need to check that the sample sizes n1 and n2 are large enough, which is the case if both samples have at least 10 successes and 10 failures. Here's the formula for the pink standard error for a two-sample test of proportions. It's the square root of p hat sub c times q hat sub c times the sum of the sample sizes reciprocals. P hat sub c is the combined proportion for both samples. Here's its formula. Total number of successes divided by the sum of the sample sizes. Quick example, we'll borrow this space up here. If sample 1 had 70 successes out of 100 observations, and sample 2 had 36 successes out of 60 observations, then p hat sub c, the combined proportion, would have 106 successes out of 160 observations. Add the successes and add the sample sizes. We know that q hat sub c is 1 minus p hat sub c, and that's all we need to find the standard error. Now for the more common test for means where we don't make any assumptions about the two population variances. I'll show the formula for the standard error when we know what the variances are, because when we don't know the sigma squareds, we plug in the sample variances s squared and consequently use the t-distribution. So for a two independent sample hypothesis test where we make no assumptions about the population variances, the standard error is the square root of the sum of the sample variances divided by their sample sizes. Now, the formula for degrees of freedom. I'm a little reluctant to show it because it looks so horrible, but don't be intimidated. It only has 4 terms: the 2 sample variances and the 2 sample sizes. Let me make a few substitutions. I'll borrow this space down here. Notice these terms with variance over sample size. We'll replace them with blocks of the appropriate color, green for sample 1 and orange for sample 2. This appears to simplify the formula. The closer the 2 variances and sample sizes are to each other, the closer the degrees of freedom will be to n1 plus n2 minus 2. In fact, if n1 equals n2 and s1 equals s2, then degrees of freedom will be n1 plus n2 minus 2. But as these values deviate more and more from each other, the degrees of freedom will get lower, so the critical value we look up in the t-chart will be higher. If you take a shortcut and try to use n1 plus n2 minus 2 as degrees of freedom, your critical value will be too low, and you'll reject h0 more often than you intend for your alpha level. Okay, our chart is done. We've already done 1 sample test and a 2 dependent sample test, so let's do some independent sample tests. Each year, a high school principal evaluates the effectiveness of her 2 statistics instructors. The instructors agree to give the same standardized final exam to their students. The principal wants to know if either instructor's students score significantly better than the other. This experiment has been conducted for years, and the variances of the test scores of the 2 groups, Instructor A and Instructor B, are consistently similar each year. Given the summary statistics for the most recent exam, conduct a hypothesis test to determine at alpha equals 0.02 if there's a significant difference between the group scores. Okay, this is clearly a 2-sample test. The samples are independent, and we're assuming the variances, and hence the standard deviations, of the 2 groups are equal. Step 1, our hypothesis. This is a 2-tailed test since we want to know if either group scores significantly higher or lower than the other. As usual, h0 assumes they're equal, that mu sub A minus mu sub B is 0. Step 2, we're given alpha is 0.02. Let's sketch our PDF of the sampling distribution. 2 sample tests follow the same procedure as 1 sample test. We draw the PDF as if the null hypothesis is true, so its mean is mu sub A minus mu sub B. Alpha is 0.02, and the alternate hypothesis, not equal to, tells us this is a 2-tailed test, so we put alpha over 2 in each tail. Step 3 is to identify and evaluate the test statistic. We have 2 independent samples whose variances are assumed to be equal to each other, but whose value we don't know. Since we don't know sigma, this will be a t-test, and we need to find the t-value for the difference between our sample means. As usual, the formula for a t-test has this general shape: red sample statistic minus hypothesized parameter divided by the standard error. This gives us our samples point on the PDF for us to compare to the critical value. The red sample statistic is x bar sub A minus x bar sub B. 78.2 minus 79.4 equals negative 1.2. The hypothesized parameter comes from h0. For 2 sample tests, this is usually 0, since h0 assumes there's no difference between the populations. That leaves the standard error. Let's look back at our chart again. We have independent samples, and population variances sigma are assumed to be equal. So this block is what we need to find the standard error. Well, it's going to be a hike, but a short hike because we know all the variables to plug in. I'll use group A for subscript 1 and B for subscript 2. First, we'll calculate the pooled standard deviation, S sub p. N1 minus 1 is 33 because the sample size for group A is 34. Likewise, S1 squared is 6.85 squared because the standard deviation of group A is 6.85. N2 minus 1 is 51 because the sample size for group B is 52. S squared is 6.44 squared because the standard deviation for group B is 6.44. The denominator is N1 plus N2 minus 2. This gives us a pooled standard deviation, S sub p, of 6.64. And knowing S sub p, we can find the standard error with this equation, and we get a standard error of 1.46. Now we can finish the calculation of the test statistic, the t-score of our sample statistic of negative 1.2, which is negative 0.819. We'll put it here in the left half of our sampling distribution since it's negative. Step 4 is to compare the test statistic to the critical value to determine if the test statistic is in the rejection region. The critical value is here at the boundary of alpha. Using the t-table, it's easy to find the scores of probabilities in the right half of the PDF. So we'll take advantage of the t-curve symmetry to find the positive version of our negative critical value. The cumulative probability we'll look up is 0.99, which is 1 minus this tail. We'll also need degrees of freedom, so let's take a peek at our chart. N1 plus N2 minus 2. Sum of sample sizes minus 2, so 84. This t-chart has 80 and 90 degrees of freedom, so our t-score will be between these two rows in the 0.99 column. Neither of these values is near our test statistic, so we'll just say the critical value is about 2.37. So, positive 2.37 here means the reflected critical value over here is negative 2.37. This is beyond the test statistic of negative 0.819, so the test statistic is not in the rejection region. We fail to reject the null hypothesis at the 0.02 significance level. The sample did not provide significant evidence that the students of the two instructors had different average scores on the standardized final exam. Okay, let's revisit our battery example from the prior videos. At a 0.05 significance level, do these sample statistics indicate that the battery populations have different average lifetimes? Here are the sample statistics from prior videos. I'm using the subscript U for us and C for competitor. It's okay to use meaningful subscripts to help distinguish between groups. We aren't given a direction to see if one sample is greater than or less than the other, only to check if they're different. So the alternate hypothesis is mu sub us not equal to mu sub competitor. And the null hypothesis is mu sub u equals mu sub c. We're given alpha equals 0.05. This is a test of two independent samples, and we aren't given any assumptions about either population standard deviation. So this will be a t-test with sample statistic x bar sub u minus x bar sub c, minus the hypothesized difference, 0, divided by the standard error. For two-sample tests, this term is usually 0, since h0 mentions 0, no difference. But it's a good idea to at least write it down so it matches the format for one-sample tests. So you just need to remember the same format for one- and two-sample test statistics. To find our test statistic t, we just need the standard error. Let's go back to our chart. We have independent samples with no assumptions regarding the standard deviations. So here's our formula for standard error. Again, there are only 4 variables, and they're all right here in our summary statistics. Plug in, and we get a standard error of 12.6. Now we can fill in the formula for the test statistic t. The sample statistic is the difference between the sample means, 386.5 minus 368.8, minus the hypothesized difference, 0, all divided by the standard error, 12.6. This yields a t-score of 1.4 as our test statistic. Step 4 is the test statistic in the rejection region. We'll use a t-table to find the t-score of the rejection region boundary here. The cumulative probability we'll look up is 0.975, which is 1 minus the right tail. Degrees of freedom is a little more cumbersome. Let's consult our chart again. Here's the formula for degrees of freedom for two independent samples where we don't make any assumptions about the standard deviations of the two populations. Statistical software will do these calculations. I'm just trying to show the reasoning and help you understand the concepts. Again, there are the same four variables, and we know them all from the summary statistics. Plugging in the values yields degrees of freedom of 39.2. When we get a fractional degree of freedom, it's usually considered best practice to round down so your critical value isn't lower than appropriate. If your critical value is too low, you'll reject H0 more often than alpha. So in the t-table, we'll look up a cumulative probability of 0.975 with 39 degrees of freedom and get a critical value of 2.023. As we can see on our PDF, this is out beyond the test statistic of 1.40, so the test statistic is not in the rejection region. We fail to reject the null hypothesis at the 0.05 significance level. The samples did not provide significant evidence that there's a difference in average battery life between our batteries and our competitors. Now, I need to talk about type 1 and type 2 errors. When we conduct a test and make a decision to either reject or not reject the null hypothesis, there's always a possibility that our decision is wrong. In fact, when we set up our sampling distribution PDF and put the rejection region of size alpha in one or both tails as appropriate, we said that if the sample statistic happened to fall in the rejection region, that we would reject H0 in favor of H sub A. But let's think about that for a second. Remember from video 1 that the sampling distribution reflects all possible samples of a certain size. So even when H0 is true, we'll still occasionally get sample means out in the tails. So if H0 were true, our testing procedure, in the long run, will incorrectly reject it some percentage of the time. How often will this happen? Well, the answer is alpha. Alpha represents the area or probability out in the rejection region. So if H0 were true, then in the long run, the sample statistic will, by chance, be in the rejection region alpha % of the time. That's how we choose alpha. I've been making up common levels of significance for our sample problems, 0.01, 0.02, and 0.05. But the value is chosen to reflect our level of aversion to incorrectly rejecting H0. Rejecting a true null hypothesis is called a type 1 error. The number that describes the error type is always a Roman numeral. I'm not sure why. If we're considering rejecting a reliable manufacturing process, medicine, or medical procedure, we want to minimize the risk of a type 1 error, and we'll choose a lower level for alpha. Every statistics textbook and lesson on hypothesis testing includes a chart like this, showing a 2x2 table of the possible outcomes of a hypothesis test. The way I've set up this chart, the horizontal axis describes H0, either true or not true, and the vertical axis describes the results or decision from our test, either reject or fail to reject. So this cell represents a type 1 error, rejecting a null hypothesis that's actually true. Assuming the null hypothesis is true, this cell's probability is alpha. Alpha is called the significance level. The cell next door does not reflect an error situation. It represents rejecting a null hypothesis that's not true. Okay, no error. We'll get back to this cell in a moment. And this cell does not reflect an error. It represents the case where we don't reject a null hypothesis that is indeed true. And as you might expect, this cell represents a type 2 error, when the null hypothesis is not true, but our test fails to reject it. The probability of this happening is called beta. That should be easy to remember, type 1 and type 2, alpha and beta. Beta is the probability of failing to reject a false null hypothesis. Let me show you how that happens. Here's our null hypothesis and the sampling distribution we'd expect if the null hypothesis were true. And based on the problem statement, this is a right-tailed test. Well, unknown to us, H0 is actually false, and this gray PDF describes what's really going on. The true population mean is over here, but we don't know it. So the sample we draw is from this true gray distribution and has nothing to do with our hypothesized white PDF. But due to chance, our sample happens to fall here in the non-rejection region of our hypothesized PDF. Since the sample is not in the rejection region, we fail to reject H0, even though it's false. This is how a type 2 error happens, failing to reject a false hypothesis. On this diagram, I'm shading beta, the probability of a type 2 error. It's the proportion of samples from the true gray PDF that fall in the non-rejection region of the hypothesized white PDF. As you can see, the value we choose for alpha affects the size of beta. Let me mark the boundary between them so you can see that if we increase alpha, beta will get smaller. And if we decrease alpha, beta will get larger. So alpha and beta are inversely related. It's easy to see and understand what alpha and beta mean on the PDF graph, and we always know the value for alpha since we choose it. But knowing the exact value for beta depends on variables we don't have. Most obviously, we need to know the true population mean. We have no idea what this is. In fact, our null hypothesis says it's over here. Beta is an idea about a real thing, the probability of failing to reject a false null hypothesis. We can understand that it's influenced by our choice for alpha, but will almost certainly never know its actual value. Alpha and beta each represent likelihoods of making incorrect decisions, so we'd like to minimize them. But there's only one way to decrease beta without increasing alpha, and that's by increasing the sample size. Remember, the central limit theorem tells us that the standard deviation of these sampling distributions are the population standard deviation divided by the square root of the sample size. So as the sample size increases, the PDFs get narrower. This reduces the overlap between the PDFs, which is where type 2 errors occur. Now let's get back to our chart for a little more vocabulary. The two columns add up to 1. When H0 is true, we either reject or fail to reject. We reject with probability alpha. So we'll fail to reject with probability 1 minus alpha. I'll shade this probability dimly because it doesn't get much attention in hypothesis testing. But the other column has a new vocabulary word. The probability of its two cells also add up to 1. When H0 is false, we either reject or fail to reject. We fail to reject with probability beta, so we'll reject with probability 1 minus beta. There are 6 vocabulary words on this chart: type 1, type 2, alpha, beta, significance level, and a new vocabulary word called power. Power is 1 minus beta, the probability that a hypothesis test will reject a false null hypothesis. Don't get confused and think that since alpha is significance level, that beta is power. Power is 1 minus beta. And while this chart is up, let me ask a tricky true or false question. Alpha is the probability of rejecting the null hypothesis. It's tricky because it sounds like the truth, but it's false. The truth is, alpha is the probability of rejecting a true null hypothesis. Similarly, the power of a test, 1 minus beta, is not the probability of rejecting the null hypothesis, but of rejecting the null hypothesis when it's false. I have one more illustration that I think might be helpful to show the difference between failing to reject the null hypothesis, which we do, and accepting it, which we don't do. Suppose you're selected to serve on a criminal trial jury for a serious offense. I'll draw a PDF on which we'll place our thoughts. The null hypothesis, H0, is innocent. In this scenario, the alternate hypothesis is guilty. We'll assume H0 is true unless we have significant evidence to the contrary. The judge instructs the jury to vote guilty only if they're convinced of the accused's guilt beyond a reasonable doubt. In your mind, you quite rightly translate this into a very low alpha. Now, there's no reason to draw a normal PDF. I'm just showing the situation in a familiar context. Here's a color scale denoting, based on the evidence presented to you, your judgment of the likelihood of innocence as green at the null hypothesis and the likelihood for guilt as red out in the rejection region. Your opinion starts here at the null hypothesis and shifts around as you hear evidence from both sides. You hear some condemning evidence, and as it turns out, by the end of the trial, you land here, deciding that the prosecution fell just short of removing reasonable doubt at your significance level alpha. The evidence against the defendant was strong, and you think it's more likely that they're guilty than innocent, but staying true to your alpha, you vote not guilty. After the trial, a throng of reporters ask you on TV why you think the accused was innocent. Is this a fair question? When you voted not guilty, were you saying you thought the defendant was innocent? It's the same with hypothesis testing. When you fail to reject H0, you're saying there wasn't significant evidence to reject it. You're not saying you think it's true. All of hypothesis testing is taking your sample statistic, converting it into a test statistic, and comparing that to a critical value determined by alpha. Always draw a PDF to guide your path and thought process. One sample tests are very straightforward. For two sample tests, you need to know how to determine the standard error, because you need to calculate your test statistic from the sample statistic. And you need to know how to determine the degrees of freedom for means tests, because you need it to look up the critical value in a t-table. I hope this series has been helpful and enlightening to you. I'm Dennis Davis. Thanks for watching, and good luck with your studies.